In this demo, we're going to be talking about geometric theorems. Geometric theorems are very important to a scenic artist because a lot of times we have to draw things that are very crisp, very clean, and based on geometric perfection, essentially. So it's very important to have a firm grasp of some geometric theorems. So we're going to go over some of those here in this little talk. The first one we're going to talk about is how to find a line that's perpendicular to another line. That's very, very important. So think of this. You've got a drop that's 20 foot by 50 foot. And you have measured the top of it, measured it at the webbing, and found the center point of the drop. Now, in order to draft anything in scenic artistry, to begin that cartoon, you have to have two baselines. You have to have a horizontal baseline, which in the case of a drop is usually the bottom of the drop, right? And you have to have a vertical baseline, which once again in the case of a drop is usually the center line, right? That ends up resulting in the composition that's drawn on that drop, no matter like what the variations of the size of the drop might be, that composition ends up on stage in exactly the position that the scenic designer expected it to end up at, centered and in the proper relationship to the stage deck. So finding that perpendicular line is really important. Also, in drawing just about any form, you need to be able to find one line, once again, that's perpendicular to another line, because that's how you are able to plot your points, right? It's over this far and it's up that far, right? That's very, very important. So I'm going to show you two ways to find one line that's perpendicular to another line. The first theorem that I'm going to talk to you about is the Pythagorean theorem. So the Pythagorean theorem, Pythagoras was a Greek philosopher and supposedly a member of a secret society of mathematicians, and the Pythagorean theorem ended up in Euclidean geometry and Euclid's theorems, okay, as one of the bases for the beginning and establishing of the whole treatise of Euclidean geometry. If you look up the Pythagorean theorem, you're going to see something that looks like, well, you're going to see a couple of things. You see one thing that looks a little bit like, not a little bit, it looks like that, right? A2 plus B2 equals C2. Okay, I'll get right on that, Susan. Some of you are probably smart enough to figure this out. My father was smart enough to figure this out. I don't go past geometry. Like, when we got into algebra, and we got into, like, I didn't even, like, wander into calculus or trig. I was like, no, doesn't work for me. So there's another way to think about this. And if you look it up online, you'll probably find a triangle, right? And you'll find boxes on either side of this triangle. And the boxes will be divided up. You'll find one box that's divided up into three. You'll find another box that's divided up into four. And you'll find another box that's divided up into five, okay? That's the easiest way to think about this. 3, 4, 5. So suppose we were dealing with feet here. We would be dealing with 3 feet, 4 feet, 5 feet. That's all you have to remember. 3, 4, 5. You choose a denominator and you multiply it by 3, then 4, then 5. So 6, 8, 10. See where I'm going here? 9, 12, 15. Okay? That's all you have to do is just choose the denominator that works best for the scale of the project that you're working on, and then multiply it by 3, 4, 5. Okay? So if you have a 20-foot drop and you want as long a line, you want to project out a point that's perpendicular to another point at the webbing of the drop, right? Then 15, right? Go for 15. You can go for 20, but then you'll be fighting the pipe pocket, right? So 3 times 5, 15. That's a pretty good projection of a perpendicular line, and then you can just extend out that last 5 feet with a snap line or with a line stick. All right. So we're gonna find a point that is perpendicular to this point here on this line. So I have this trusty yardstick here, which is very useful for dealing with chalkboard demonstration, and I'm going to use that right now. So I'm going to do 2 at a time, right? So I'm going to go from this point here, I'm going to go and do my 3. So I'm going to and there's my point on that line. Now here's where it gets a little tricky. Not tricky, really, but this is the thing you need to know. So this is my first line, and all I have to do if I was using a measuring tape was just measure straight out and go 6 feet. Simple, right? Now, when I go up from that point, this is the fun part of doing this on a chalkboard. We'll do it this way. So I'm going to center that point there. What I need to do is I need to draw a little bit of an arc, right? Then I'm going to go back to my original point. I'm going to center this point on that hole there. And I'm going to do an arc, and where the 2 arcs cross, that's my point, where I will find a line that is perpendicular, width of the chalk here, perpendicular to my first line, okay? So this is 3, this was 4, and then this hypotenuse here, was 5, okay? So 3, 4, 5, okay? Now, suppose it's smaller. We're not dealing with 20 feet, right? We're dealing with 4 feet, right? Like, I don't want to have to do the whole 3, 4, 5 thing just for 4 feet. So there's another way to find a perpendicular line. So I want to find a line, once again, I want to find a line now that's perpendicular to this point. So what I'm going to do, and this, we're going to be working with this bad boy a lot, right? I don't even have to measure. I don't have to measure anything, right? I just open the compass up a little ways, and I put my compass point on the point that I want to find a perpendicular line to, right? Like so. And then I open my compass up wider, and I come to this point, and once again, draw an arc, and then I go over here, and I draw an arc, and once again, where those two arcs cross, I have found my line that's perpendicular to my baseline. You can do so much with a compass. Compasses are amazing in terms of finding forms, in terms of finding, ratios, and we're just going to go through a few of those here. All right. So the next one we're going to do I'm going to draw a circle, and anytime I draw a circle, I want to make sure to mark my compass point. You don't lose track of your compass point. Hang on to it, right? Make sure that you know where that bad boy is at all times. Because nothing's more frustrating than needing to find a compass point, and you have a circle drawn on a drop, and you need to find that compass point again, and having to grope around for it and go, right? So always keep that compass point. So let's draw our circle. There we go. Okay, so we have a circle. I want to find my vertical baseline and my horizontal baseline in this circle. So what I'm going to do is, it's really easy. One line, I can just draw a line through the compass point, right? And I know that that line is in the center of the circle. And no matter where I put this line, I'm still dividing that circle exactly into two halves. Can't do anything else. But now I want to find a line that is horizontal to that. So we're going to do what we just did, except that we don't even have to measure out. Remember, like with that first line, we measured out and we found these points. Those points are already established for us because it's a circle. So now I can just go to where that first line crossed the circle, and I can draw an arc. And then I go up to this line up here, and I cross that arc. And then, when I go through the intersection of that arc and my compass point, I have found a line that is perpendicular to my initial baseline. Okay, so I've divided the circle up evenly into fourths. So that's called bisecting a line. When we found a line that was perpendicular to another line, or in bisecting the form, it's the term is bisect a line. Okay, so now the thing that's cool about geometry, again, if we wanted to, right, having done this, we can actually draw a square inside this circle just from the points of these two perpendicular lines. We can actually draw a perfect square, right? So understanding this is important because I want you to understand how we can actually use a circle to create a lot of other geometric shapes. So now suppose I didn't want a square, I wanted an octagon. What I can do is I can actually, once again, bisect a line. So I'm going to draw an arc, and then I'm going to draw another arc, right? And I'm going to do that over here too. I'm going to draw, oops, wrong point, draw an arc, and I'm going to draw another arc. I didn't quite draw that arc deep enough. There we go. So where those arcs cross, that's the perfect halfway point of my quarter. So effectively, I can divide this form up into eighths now. So just by going through those two arcs, and then again through my compass point, right? I can bisect, cut up the pie even deeper, right? And actually I need to do this because I need to have that point on the circumference of the circle. So, and then all I have to do is go from point to point. And I've created an octagon. So now, understanding this is how we're going to learn how to make even more shapes using a circle. All right? So let's play around with the circle a little bit more. I don't want to divide it up into something that's divisible by 2 or 4. I want to divide this circle up into something that's divisible by 3. Actually, I think I'm just going to erase the whole thing and really quick compass it again so that we keep it pretty straightforward. This is the hard part about doing it on a chalkboard. Usually I get to just move over to another piece of the floor when I'm demonstrating this. All right, so fresh circle. We're going to do the same thing again. We're going to go ahead and I've got my compass point right here. Now I'm actually not going to bisect the line this time, okay? I am going to use the radius of this circle to find a hexagon. There we go. All right, so here's my radius, right? Okay, so what I'm going to do is go out to either end of the diameter. I'm simply going to do that with the radius, okay? If we wanted to make it really, really clear, I draw the arc all the way through, all right? And then I'm going to do this here and that there. And then once again, from those points where that radius crosses the circumference of the circle. And now I've drawn a hexagon, okay? For my next trick, I'm going to draw a star, starting with a pentagon. Okay, and for this exercise, once again, I do need to bisect. So I do need to find my vertical and my horizontal baselines again. So I'm bisecting that line. All right. Now I'm going to bisect this line right here. I need half of that. There it is. Then, from that point, I'm going up here, and I'm finding this distance. Oops. Drawing an arc down to here. Then from there, I'm drawing an arc up to here. Okay? So, bisected this line, went from that point, went up and found this distance here. I keep wanting this to be more flexible than it is. From this point to that point, then drew an arc down to here, and then came here, found this arc here. From this point down to where this arc intersected this line over here. That distance, right? That's the distance that I need to divide this circle, this circumference, up into fifths. And then just to check it, yeah, it's a little bit off. It's chalk. So it's going to need to be a little bit longer. Let's double check this. That's the problem right there. Okay. Oops. Also helps if you keep compass where it belongs. That's better. Okay. So I can draw a pentagon. Now, in case you're having a hard time, oops, went to the wrong thing. In case you're having a hard time following this, remember, you all have little computers in your pockets. They're called cell phones. And you can get all sorts of cool stuff on those cell phones, including how to draw a pentagon inside a circle. And then from that, it's really easy to get your star. Okay? So there's a couple of other things that I want to show you now working with paper. But I do want to remind you that all of this, all these geometry theorems that I've been showing you are in the document that is loaded up in the cartooning section, How to Cartoon a Backdrop, written by Howard Jones and myself. Also in the PDF of the book that I wrote with Peter Budare, Scenic Art for the Theater, you have a whole chapter on cartooning, and there are many more geometric theorems in terms of how to plot out arches and discussions of various ways of cartooning, which we will be going over in these demos as well. So make sure that you reference those materials. All right, so we're going to talk a little bit about dealing with paper and cartooning. And one of the first things that I wanted to make sure that I didn't forget to point out to you is this is a cutoff from a piece of just a run of brown paper here in the shop. This is the factory edge right here, okay? The factory edge of brown paper or butcher paper or whatever is usually pretty straight. So we were just talking about how to do perpendicular lines. Well, if you're dealing with a piece of paper and you want to find a perpendicular line, you can actually just use the factory edge and do a really careful fold where you make sure that the factory edge lines up like so. And get a line that is nice and perpendicular to the factory edge of that paper. So don't forget that. You can also use a piece of material that's actually square, like a 4x8 piece of stock. And a lot of shops have oversized square rulers in them, or square triangles that are built for use in the shop. This shop does not. I'm going to try to get on that one of these days, but we just don't have those right now, bit by bit, right? Do not trust stage jacks to be square, because not all stage jacks are built the same, and some of them are actually built to tilt back just a little bit. So be careful about trusting stage jacks to be absolutely at right angles. So what I'm going to show you right now, and this is just another fun thing. So supposedly, back to stars again, supposedly Betsy Ross when she was being like interviewed to be the seamstress of the first American flag, was asked if she knew how to make a really like clean looking star, and supposedly this is what Betsy Ross did. So goes the legend. So I folded this piece of paper in half. I'm going to fold it in half again, and I'm making sure that my folds are really, really clean, corner to corner. I'm keeping factory edges together, right? And then I'm just cleaning them up with an edge of scissors. So now I'm opening this piece of paper back up. And what I'm going to do, so I've basically folded this piece of paper into even fourths. Now with it folded in half like this, and this is also loaded up in your cartooning section, I'm going to fold the corner of the paper down to where one of those quarter folds are. Once again, make sure I have a crisp edge. And then I'm going to fold this small side of the triangle in. And then I'm going to fold, and the thing that you'll find is that when you fold over that section there, it actually matches up. Then making sure that I keep an eye in here on where that corner is, because I don't want to go out past that corner. You have to make sure that you're cutting on the side of the paper that has, see this side has got extra folds in it. You don't want that side there. You can pull it apart. You want the side that just is a single fold. I'm going to start making sure that I stop at that corner, and I'm simply going to make a cut. And then when I take that piece of paper and unfold it, I have a star, okay? And you can open it up and go, oh, I want my star, I want those lines to feel a little bit more like they're parallel. So I can actually fold it back up if I want. And make it just a little bit, oops. Deeper. Okay. All right. Okay, I'm going to do one last demonstration for you in terms of doing geometric tricks. And this one is for making an oval using string and screws or nails and a compass. All right, so I'm going to point you now to my work surface. There we go. First thing I'm going to do is I'm lining up the edge of the paper so that I get one of my axis lines, and just like so many other geometric forms, we need two axes. All right, now I'm going to use my compass to bisect a line. Actually, just to make sure that I'm sort of in the middle of the paper, I'm just going to do that so that I know I'm fairly well centered in this not particularly evenly cut piece of paper. So I'm going across that axis line, doop-ba-doop, opening up my compass a little bit so that I can go bloop. And where those two compass points cross, that is where I will have my other straight line. And I forgot to bring a straight edge with me, but this is the beauty of working in the theater. One can almost always find a straight edge. I'm going to draw this axis out. All right. Now I need an oval that is 2'2" by 2'9". So what I'm going to do is I'm going to measure, boom, boom, sorry about that. There's little flies all over the place. Okay. So I'm going to measure up on this axis. So 2'2", right? It's going to be 2'2" this way and 2'9" that way. So I need to measure up 1'1". All right. And then the other thing that I need to do is I need to take my compass and I need to have my compass radius, right, be half of the long axis line, all right? So that's 1 foot 4.5 inches. So here's my 1 foot 4. It's pretty darn close already. Close it up just a little bit more. Jenga. Okay. So then I'm going to put my compass on that point that is half my height of my oval. And I'm going to draw an arc across my long axis line, all right? So I have 3 axes here, all right? And actually, just to make my life a wee bit easier, I'm going to flip the paper around this way. So what I'm going to do, and this is, to be honest, not the easiest thing to do on our paint deck because our paint deck is one layer of Celotex that goes in, that's directly on top of a concrete floor. So you can't get much traction in terms of nailing or screwing into our paint deck. Not sure I'm going to get much traction here either. Okay, hold on a second. Hi there, sorry, back now. The problem was those were metal screws and they weren't biting. And so I went to my road box and got actual wood screws. So what we're going to do now is we're going to take a piece of string. We're going to tie this string around these 3 screws. You want the string to be tight, but not like, you know, banjo, guitar string tight, right? All right. Try and tie Tie a forgiving knot in the string, because I'd like to use this string again. Literally, and again and again and again. There we go. Yeah, okay. So it's tight, but it's not like ridiculously tight, okay? I'm just going to give myself a lot of extra string here. So I'll be dragging this around. Now I'm going to pull this, take this screw out. I'm keeping the screws in on the long axis of the oval. All right. I'm going to take my charcoal. And all I have to do is go around. You want to make sure the string catches. Screw, and I simply go around. Oh, I missed the screw. See what happens? There's the screw. Right. So, yay! And we have an oval. All right. Isn't that the coolest trick ever? Now, I actually want to draw an oval that is narrower now than this, narrower and shorter than this, that goes on the inside of this. So I'm going to stop the film and then redo it, and then restart it so I can fast forward it, and you can see me draw an oval inside the oval. And that's the end of stupid geometry tricks. Learn them, practice them, have them at your fingertips, and it will help you through so many cartooning and geometric conundrums. All right, thanks. Bonus piece. Looping up a snap line. Okay, ready for this? This is the helicopter method. Why do we use snap lines like this? We use snap lines like this because if you use chalk boxes, lots of charcoal comes out of the chalk box and it just goes bleh, you know. So we can use the same chalk boxes that the carpenters use with their nasty blue chalk, which never erases off of scenery, by the way. And every time that string comes out, that line comes out of the chalk box, it just goes blah, 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 you know, and like throws powdered charcoal all over our drop. So what we do is we stretch snap lines out and we take a jumbo piece of charcoal, just put a little divot in it and pull it along the line, and that's called chalking a line. All right? But then here's the problem, is that people who aren't used to using snap lines, and you can see by the way this one is like kind of sort of not really very well wrapped. Here, we're just going to unwrap the nastiness there, all right? And still, like, it's like someone has like looped it around the long way, right? Okay? This takes forever to do, right? You're like, all right, so what we do is we helicopter it, all right? Once you get it down, you'll have it forever, all right? And it loops up the snap line on the line stick on so much faster. See, all of it's already done, okay? You can see where it's crisscrossed there, all right? So practice it. At first, you'll be like, ah, you know, all right? But once you finally get it, once the motor control kicks in and that impulse, that electronic impulse only has to go from your hand to your spinal cord and not like all the way up into your brain going, ah, like that. It's just like boop, 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 right? You'll be able to loop these snap lines up at not the speed of light, maybe just the speed of sound. Okay, so much for the bonus round.